Tonight we're looking for all natural numbers in such that 36 raised to the nth power minus 6 happens to be the product of three consecutive, and these are positive integers, folks. Natural numbers, positive integers are synonymous. So let's try it out for a small special case and see what we get. For n equals 1, you get 36 to the 1 minus 6 equals to 30. And I'm going to just write it down to save a little bit of time. This is never equal, and it's very easy to check because it's a small number. This is never equal to, let k be a positive integer. This is never equal to k times k plus 1 times k plus 2. Again, k is just some other integer, positive integer. Okay, and this is very easy to check. Just check it for, let's say k equals 2. If k is equal to 2, you get 2 times 3 times 4, right, which is 24. So that's less than 30. Now, if k is 3, you get 3 times 4, which is 12 times 5, which is 60. So you see 30 misses the train. All right, so it's clear it doesn't work for n equals 1. N equals 6 is a little more involved, and it's not quite as clear there. So we need to come up with another, as n equals 2, excuse me, I don't know what I said, but n equals 2 is a larger number, and it's harder to check manually. So we need to come up with a better approach that doesn't involve, huge computations. And so this part right here is a little hard to see, but it is motivated by the fact that 36 minus 1 is divisible by 7. 36 minus 1 is 35, and that's divisible by 7 since 35 is 5 times 7. Now, this is congruence arithmetic right here, or modular arithmetic, and you can treat it much like regular equality. Notice that if you just multiply this against itself n times, you get 36 to the n is congruent to n. People try to prove this by induction or other things in number theory course, but really it's a property of equality. Congruences and equality are very, very similar in structure. So again, you can multiply this simple truth here by against itself n times to get this statement. And there's a little bit more justification for it than that in a number theory course, but for now we'll take that as the truth, okay? So we know that 36 to the n is congruent to n mod 7. 36 to the n is congruent to 1 to the n mod 7, 1 to the n, of course, 7. And so right here we have this following statement. We can replace 36 to the n with 1 to the n. Now, why can we replace negative 6 with 1? Well, 1 is congruent to negative 6. Y'all remember the definition of negative 6 right here? 1 is congruent to negative 6 because 1 minus negative 6 is 7. And that's what we mean by congruence. A is congruent to B if A minus B is divisible by some multiple of 7. Okay, so 7 is certainly divisible by itself. So 1 is congruent to negative 6 since 1 and negative 6 are 7 apart on the number line. So you see how negative 6 got replaced with 1, all right? And so what we get is this super simple statement here. 1 raised to the n is always 1, right? And plus 1 is 2. So we get that 36 to the n minus 6 is always congruent to 2, okay? And you'll notice that is the case with 30, right? 30 is equal to 4 times 7 plus 2, right? So that's the same 2 that you see right down here, 4 times 7 plus 2. Okay, that's the same 2 you said here, and a 2 would happen for any n according to a modular arithmetic, all right? So we know what's going on with this expression, modulo 7. We know that it's always congruent to 2 for all natural numbers n. Okay, so now we are talking about such that this is the product of 3 consecutive natural numbers. So I wrote down the product right here. And all we're going to do is consider these modulo 7. Now, I just created a table for you here, folks. 0, 1, 2, all the way through 6. Technically, we don't have to do it for 0 since we're not interested we're only interested in positive integers. But just for the sake of completeness, I did it. And again, you could see it. It's k, and then k times k plus 1, k plus 2, reduced modulo 7. 6 is itself, modulo 7. 2 times 3 times 4 is what? Is that 6 times 24? Divide 24 by 7, you get a remainder of 3. That's this 3 right here. Now, if you want to do this a little bit simpler, notice let's just do it for these larger numbers here. 4 times 5 is 20. Now 20, or let's try maybe 6 times 4. Okay, let's do it like this, folks. So I'm going to do 4 times 6 is 24 times 5. What I'm trying to do is avoid quote a large multiplication. So this is 24 times 5, right? 4 times 6 is 24. And then you have 24 times 5. But notice that 24 leaves a remainder of 3 when you divide it by 7. So you get congruent to 3 times 5. But 3 times 5 is 15, and it leaves a remainder of 1, right? So that's how you do modular arithmetic. You never have to do any particularly large multiplications if you just work on the inner pieces. And these are trivially 0 since 7 is congruent to 0, right? 7 is congruent to 0. 7 minus 0 is 7, right? So, but what's the takeaway here, folks? Well, we know that this piece right here is always congruent to 2 modulo 7, but we do know from this table, this tabular format, we know that k times k plus 1 times k plus 2 is never congruent to 2. See, and technically I could say done right now. Okay, because k times k plus 1 times k plus 2 is never congruent to 2. Okay, let me put the inverted negation here, the negated relation, not congruent, just like not equals, okay? So you see, that means that can't happen, all right? We're done. I could say QED right now, since we know that this object always leaves a remainder of 2, all right? This object always, this guy right here always leaves a remainder of 2 when divided by 7, and 3 consecutive integers never can leave a remainder of 2, right? Okay, so I could say QED next video, right? But I'll just go ahead and be a little more thorough about it. So if 36 to the n minus 6 is equal to 3 consecutive integers, then they're certainly congruent to each other, but this is impossible because this side right here is congruent to 2 for all n, and this side right here is never congruent to 2 for all k. Right? So that's just like in equality sense, trying to say that 2 is equal to something other than 2. All right? You can think of it like that. It's that simple, really. So that concludes the proof. And what is the conclusion? The conclusion is there are no solutions. It can't happen. All right? The instructions are faintly misleading, but the answer, there are no. There are no solutions. There are no solutions to this. No natural number n satisfies this condition. Okay. See how that's it. Now I'd like to see. There's a lot of people don't like modular arithmetic, don't understand it, never been taught it, never taken number theory. I'd be interested in seeing a proof of this that was just, quote, more elementary and didn't use modular arithmetic. It probably exists. I just like the compactness and the notational efficiency of modular arithmetic. But anyway, that's it. And there are no natural numbers in such that this condition prevails. Okay? Thanks for viewing.